So our next speaker is Konstantin Olmezov from the Moscow Institute of Physics and Technology, who speaks on additive energy of convex sets with higher concavity. Please.
Okay. Hello, everyone. I want to speak about higher concavity, and this is not typing error. I really speak about method where higher concavity is more useful, assuming than higher convexity, as usually. We study typical objects, some set, and additive energy. I think it not need to be defined in details. And I use color for improve navigation of your attention inside formulas, inside equations. Color is not word, color is not part of statement. This is just addition. This is just secondly part of slide. We say that set of numbers is called convex if consecutively differences is increasing. And main question in this area is what we can say about the size of some sets. For example, we can consider geometric progression. I'm sorry, I need pause few seconds. I'm sorry. Okay, I can continue. We consider as example geometric progression, and we have extremely growth of consecutively differences here. And we can say that some set of such progression contain shifts of prefix of progressions. And we can use this fact for obtain a lower bound of some set size. Such lower bound will be described as sum of consecutively natural number, and we obtain extremely bound finally. If we consider other example such as squares of numbers, we cannot use such method for obtain very good lower bounds. If we use such method, we have very slightly growth of size of blocks between two consecutively elements of sequence, and we have only power 3 divided to 2. And it is not really bound because famous number theoretical results say to us that that very strongly bound is true for this set. So we have interestingly question. Is it really to generalize such strongly bound to all convex sets. And actual conjecture ask about bound of additive energy, of course. This is more strongly question that question about size of some set. Here I describe actual results. It is not finally. We have many work in this area. So for describe my result, I need some notation about consecutively difference. Firstly, I provide a discrete analog of derivation, and I'm sorry, a few seconds. Yes, and I provide Hagley derivative, so, and describe convex sets in these terms. So I say that set is convex if secondly discrete derivative is positive in any point. And I study sets with non-positive third discrete derivation and not positive fourth discrete derivation, and I obtain strongly bound for energy of for additive energy of these sets. I say only a few words about history. Exist two main approaches for obtain bounds. For obtain bounds of some set and energy of convex sets. First, very powerful approach is incidence geometry. We not say about it today. However, it is very, very powerful approach, and we can obtain very strongly bound from this approach. But today we speak about arithmetic approach that provided by Garayev 20 years ago, and this approach have not next steps, have not new results on this course, and I prove some partial result. Main part of this approach is idea that we can merge and summing inequality from definition of convex sets for obtain new inequalities. See to fall line on slide, and this inequality provide some avoiding of tuples that should be indexes of elements in solutions of equation from definition of additive energy. And we need some term Garayev equation, and Garayev obtain bound for this for number of solutions of this equation. Garayev bounds is Ln, and it is proved trivially by chain of inequalities for this slide. And we think that it is not best bound, and it is possible to improve it. So Garayev obtained corollary from his lemma, and bound in this corollary is very related with the bound of JL. For obtaining this corollary, we need to associate pair of representations of some element of from some set with solution of Garayev inequality, and we turn to contradiction with a contradiction between small size of some set and upper bound of JL. Here on slides, I show chain of this inequality. I will not to speak about technical details. We have not time for it, unfortunately. And replacing bound of JL turn us to replacing bound of additive energy of bound additive energy, yes. So our main target is bound for JL for number of solutions of such equation. And we have other improvement in case where we assume non-positively of fourth derivative also. So let's write a table where we describe solutions of the equation. Main Garayev idea that that values of I, that values of I and G can, I'm sorry, values of I and K can be fixed, and then exist only one value of J for which equation solution is correctly. If it is possible also, if it does not exist. This is two cases for each pair of I and K. And all this pair described in table, and in self table, we write a value of J. Okay, here I illustrate how to see this table, how to navigate between her cells. And let's go to mathematics instead of illustrations. Graph notice that in each column we have increasable values from top to bottom, and it is strongly increasable sequence, and it is mean that number of solutions that we denote as JL can be bound by number of all cells in table. For improve this result, we need to show that some cells from table need to be empty. So we need some lower bound for growth of sigma in some columns. Unfortunately, in a single column, we cannot estimate, we cannot bound growth because this very fast. It can be very fast. Counter example here is sequence with is sequence that built by recurrence. Here we define an important notation. If we write di for describe consecutive differences between elements of A, and we rewrite graph equality to such form that we can see on slide. It is very important form because we use this form in our next proofs, following proofs. So here we can see how recurrence connected different values of di. Okay, and here we see that really such value of sigma can be solution of this equation. We cannot bound growth in single column, but we can study relationship between two columns, and we can speak about differences between sigma from two columns and the same row. Sorry. How we can do it? Our main lemma that difference between solutions for different I have greater value that difference from values of I. For proof it, for provide proof of this lemma, we use visible of di in some line. And let's describe solution. We have two equations. First equations between sum of green points and sum of orange points, and two solutions that have that have almost the same structure. How we can use main question here, how we can use third derivatives, our assuming about third derivatives. For understand it, let's consider ask what mean our assuming about second derivatives. It is mean that differences di is increasable, and assuming about third derivatives means that difference between consecutively di is non-increasing. It is very important, and it is true also for differences between dA that have fixed distance on indexes. We can see this in slide. We, in fact, fix some distance. Here it is I2 minus I1. And I say that when I turn colors from left to right, this difference is decreasing, non-increasing, strongly speaking. And we can go from contradiction and assuming the difference between solutions J is less than or equal to difference of base indexes I. From provide this assuming, we turn to propositions that that two differences between corresponding values of di have some inequality than we can see on slide, and then we can summing these inequalities and derive fact that k is less than L. That is trivial fact from a chain of inequalities from definition of convex sets. This fact this fact turns us to such inequality between differences of sums of values of di that is differences between consecutively elements of A. And finally, we can use this for Bio's contradiction, because when we select when we define J1 and J2, we talk that this is solutions of equalities, and now we have inequality. so by rearranging terms from side to side, we can build inequality that contradict with these equations. Okay, here we have some horizontal inequality and no, vertical inequality. And here we have horizontal equalities that can be summing and turns out to contradiction. I have not time. That's final of proof of our lemma, and I need 1 minute for talk about using of this lemma. We just provide induction for understand that if we have many such rows, one under other, that we improve additional term from 1 to some variable, and so we can describe blocks where distance between two existing solutions, between indexes for which they exist, this difference are fixed, and summing result on these blocks, we can turns to our final bound. I'm sorry, I have not time for talk about all details.
Okay. Thank you very much. I see that Peter Bradshaw has a question, and I think he can ask you directly now.
Hi, Konstantin. Thanks for the talk. I was wondering, can you get any non-trivial results if the second differences are less than 0 rather than greater than 0? So delta squared A is less than 0 rather than greater than 0.
I mean that general case where we have not assuming about third derivatives?
Yes.
No, unfortunately, I cannot have those bounds. No.
And if we assume that, if we assume something about third derivatives, what would we have to assume?
Have to have what?
If we wanted to have the second derivatives are negative, what would we have to have for the third derivatives to make it work?
I think that yes, if I understand you right. Yes.
Okay.
Oh, if we change sign on each derivatives to inverse.
Yeah.
Yes. Why not?
Okay. Thank you.
Okay. And Konstantin, Sophie Stevens also has a question. Do you think that a more complicated version of this proof and correct conditions would give results for a higher convexity?
Not. It's more. It's interesting case. I cannot analogous for higher convexity. No, I find it, but I not have it. I have not it.
Okay. I thank the speaker again for his talk. And the next talk will be